Chapter 24, Metabolism. In this first section, I'm going to cover the difference between good fat and bad fat. And as we do that, we can talk about some of the myths surrounding saturated fats and ask whether they are bad for us and what has happened to us as a society when we attempted to eliminate saturated fats from our foods. We'll talk about omega-3 fatty acids, one of the more common monounsaturated fatty acids, which are healthy for the human body. We'll then move on to talk about lipoproteins, like HDLs and LDLs. We consider LDLs to be bad cholesterol and HDLs to be good cholesterol, but the reasons that these are bad and good are more complex than the reasons that bad fat is bad and good fat is good. And we'll also talk about statins, the #1 prescribed medication, and we'll learn how they work. Or more importantly, we'll learn the physiology of the human body behind how these drugs work. Chapter 24 can be summarized by this picture here. So you got it? Okay, we're done. End of chapter. Ha 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 ha, just kidding. But that previous picture should illustrate something. First of all, it may look complicated, but it's actually a simplified view of human metabolism. There's no way that we could cover every one of those chemical reactions. And even if somebody knows about 50 chemical reactions that happens in the human body, they understand just a tiny percentage of human metabolism. So that hardly makes them an expert. And anybody who can name fewer than 50 chemical reactions that occur in the human body is far from an expert on human metabolism. So we're not going to become experts. Instead, we're going to take a fairly broad approach to some of the basic types of chemical reactions that occur in the human body. So we'll talk about anabolic and catabolic reactions. We'll review the Krebs cycle and aerobic respiration. And then in this first section, we'll talk about the metabolism of carbohydrates and the metabolism of lipids. Lipids are going to be a bit more complicated because we'll have to talk about good fat and bad fat, and then talk about good cholesterol and bad cholesterol, which are two very different subjects. Let's start with some basic definitions. Metabolism is all of the chemical reactions occurring in the human body. Cellular metabolism would be those chemical reactions occurring within cells. So what chemical reactions happen outside of cells? Oh, things like phosphate and calcium forming hydroxyapatite crystals to form bone tissue. That's a type of chemical reaction that occurs outside of cells. And in the digestive system, we learned about the breakdown of molecules in the lumen of the intestines. That was happening outside of cells as well. Catabolism is the breakdown of molecules into smaller ones, whereas anabolism is the building of larger molecules from smaller ones. Our cells might break down larger molecules to trap some of the energy that's released in the form of ATP. This ATP can be used elsewhere to build molecules that we need, for instance, usually from smaller ones. Any chemical reaction that ends in genesis means to build. These are anabolic reactions, where the products are larger and more complex than the reactants. For instance, gluconeogenesis is the building of new sugar molecules, glycogenesis is the building of glycogen, and lipogenesis is to build fatty acids. On the other hand, chemical reactions that end in lysis break larger molecules down into smaller ones. These are catabolic reactions. For instance, glycolysis, glycogenolysis, and lipolysis are the opposite of the three that I just described. One reason we eat food is to provide the building blocks for all of the anabolic reactions that the body must undergo. For instance, molecules inside of cells or outside do not last forever, and they will need to be replaced. Sometimes I even need more cells. My epidermis is constantly undergoing growth and replacement, as is my bloodstream. Remember, we produce 3 million new red blood cells every second. That requires a lot of amino acids to make all of that hemoglobin, and phospholipids for the plasma membrane, and some other molecules as well. And then sometimes I make things that I then just secrete from the human body, and therefore need to make some more of them. For instance, saliva, stomach acid are both excreted from the human body. The three common organic compounds that we'll be discussing related to metabolic reactions are glycogen, which are a polymer of glucose and therefore a carbohydrate, triglycerides, which are a form of lipid, and proteins. You may notice we've covered 3 of our 4 types of organic molecules that we covered back in BI 231. So why are nucleic acids left off of this list here? Well, I need to make more DNA for cell division, and every time I make a protein, I have to transcribe DNA into RNA. But we do not break down DNA or RNA to release energy, and we don't use these molecules for energy storage for later. Therefore, we can ignore DNA and RNA when we cover this chapter. Let's start with carbohydrate metabolism. This should be the easiest. We have a number of enzymes that can break down complex carbohydrates into simple sugars, such as glucose. And then glucose, as you've learned, can be broken down using oxygen by aerobic respiration inside of our mitochondria. This will produce carbon dioxide and water as our waste products, and we can trap some of the energy that's released from this catabolic reaction in the form of ATP. We don't need to remember every step of the breakdown of glucose, but a few of them will be important. Let's start with a quick overview. Glucose can first be broken down in the cytoplasm by a process called glycolysis, the products of which can enter the mitochondria to enter the citric acid cycle, or otherwise known as the Krebs cycle. And high energy electrons can be stripped from these molecules to enter the oxidative phosphorylation reactions that occur within the inner membrane of mitochondria. Let's have an overview in cartoon form. We start with glucose, which has 6 carbons, 6 oxygens, and 12 hydrogen atoms. These are all linked by covalent bonds. 2 of them over here can be traded for one another. So glucose can flip from a circular form to a linear form without losing any covalent bonds. We've just swapped a couple of them. The metabolism of glucose can be overly simplified as thus. I take molecular oxygen to strip some hydrogen atoms off of glucose one at a time. This also releases carbon dioxide as a waste product. Now, this is not literally the chemical reactions that occur, but this is basically what is happening. I'm stripping some high-energy electrons off of glucose. This will produce a water molecule as a waste product. And I can't really do anything with the carbon atoms, so I have to produce a carbon dioxide as well. From here on out, I'm going to draw glucose in its linear form, and I'm not going to draw any of the oxygen or hydrogen atoms. So we're just going to consider glucose as a 6-carbon molecule. Out in the cytoplasm, glycolysis can occur, where we break a covalent bond in this glucose molecule to produce 2 pyruvate molecules, or pyruvic acid. These are 3-carbon molecules. Next, we're going to move these pyruvic acids into the mitochondria, where we can strip away a carbon atom from each using oxygen. This will produce two acetic acid molecules, which we will link up to coenzyme A to produce two acetyl coenzyme A's. Acetyl coenzyme A would then enter the Krebs cycle, where it would join up with a 4-carbon thing to produce a new 6-carbon thing, and we strip away one carbon and then another carbon using the high energy electrons to generate some ATP in the process. But then we recycle that 4-carbon thing to join up with acetyl coenzyme A to form the 6-carbon thing again. Hence, we call this a cycle. If that whole process was glycolysis, or the breakdown of glucose, gluconeogenesis is the exact opposite. That's when we form glucose molecules, or things that are equivalent to glucose. For instance, the liver can convert lactic acid back into pyruvic acid. This requires ATP, but we consider that pyruvic acid to be equivalent to glucose, because one glucose is really just two pyruvic acids. Glycerol and amino acids can also be converted into glucose equivalents, as we will see in upcoming sections of this chapter. Perhaps you remember which hormone it was from the previous chapter that triggers the formation of glucose and its release into the bloodstream. We do this to make sure that the brain and, our other organs have adequate energy at all times. As we will see, converting lipids and proteins into glucose equivalents is a little bit complicated. However, I can't simply store glucose for a rainy day. Crystals generally don't do well in my cells. Therefore, to store some extra sugar for later, I can convert glucose into a polymer called glycogen. This process is called glycogenesis, where I glue one glucose molecule onto another and onto another until I form a large polymer. Then, later, if I need energy, I can break off one glucose from that glycogen at a time and dump it into the Krebs cycle to generate ATP. This is called glycogenolysis, or the breakdown of glycogen. Just be careful, this is going to look a lot like the word glycolysis. The only difference here is we've got this gen in the middle. So be aware that a small spelling error could make it very difficult for me to tell whether you're talking about glycolysis, the breakdown of glucose, and glycogenolysis, the breakdown of glycogen. That's all that we need to review for carbohydrate metabolism. That was fairly simple. We're next going to spend a lot more time on lipid metabolism. Lipids are easily the most misunderstood molecule in the human body. A lot of people really don't like their fat, and will do anything to try and get rid of it. Many health and fitness gurus can get rich off of this demand. And the demand is perpetual because it's very difficult to get rid of body fat. And why is that? Well, I can make the answer very simple. We need it. We need fat in all of its forms. We need lipids in our cell membranes, especially phospholipids. Fat tissue, or adipose, is useful as insulation and energy storage. Remember, we can't store sugar, and even glycogen isn't the best energy storage molecule. Fatty acids and triglycerides are going to be even better than that. And we're going to synthesize a number of hormones from cholesterol, another type of lipid. Therefore, the body is very good at forming lipids and saving lipids for later. The only way to get down to 0% body fat is, I think, to die. Your body just doesn't want to get rid of these very important molecules, no matter how much you want to get rid of them. We're going to talk a lot about fatty acids because these are a very important energy storage molecule. Not only are they stable, meaning they're going to last a long time. They won't accidentally break down over the years if we're not using them. But they also have some important properties. They're fluffy. So adipose tissue, in addition to being a good energy storage tissue, can also provide me with insulation, keeping me warm and absorbing shock in certain areas of the body, like my joints. To make a fatty acid even more stable, we're going to take 3 of them and attach them to a glycerol molecule to make a triglyceride. This is the molecule that we typically think of as fat. This is what's stored inside of adipocytes within the vacuole, and we can break down these molecules for energy later. Let's start, though, by comparing it with glucose. Doesn't have the same shape, but I have the same atoms. A triglyceride is made of carbon and hydrogen and a few oxygen atoms, just like glucose, only arranged differently and in different amounts. That's important because it's going to make lipid metabolism a heck of a lot simpler for us. We can break down lipids for energy. This process is called lipolysis. Breaking down a triglyceride would form 3 fatty acids plus a glycerol, and these can then be broken down further to generate ATP. Luckily for you, I don't have much more chemistry to go through, and that makes it lucky for me as well. To break down the glycerol component of a triglyceride is simple. We get rid of a carbon dioxide, attach a coenzyme A, and now I've got acetyl coenzyme A, which you should remember can be dumped into a mitochondria to enter the Krebs cycle, broken down further, and we generate ATP. Fatty acids are also easy to metabolize. I can take this fatty acid here and break it into a bunch of 2 carbon molecules and attach coenzyme A to each of them, and once again we dump this into a mitochondria and generate ATP. You may have noticed I had to add some oxygens. Luckily, molecular oxygen is easy to come by and quite reactive. Therefore, that was not a difficult addition. And now it's story time. Back when I was studying for my quals, one of my classmates decided to adopt an all Smarties diet for a week. If you don't know what Smarties are, they're a type of candy that are, I think, nothing but sugar and food dye. So she was on a no-fat diet for that week. Was that healthy? Would she expect to lose adipose tissue because she wasn't eating any fat? No, absolutely not. And that's because all of the chemical reactions that I just described are also reversible if the reactants are in high quantities. If you eat a lot of sugar, you could convert some of that sugar into glycogen for storage, but an even better energy storage molecule are triglycerides, and therefore glucose, if you break it down into acetyl coenzyme A, can be converted into triglycerides. A bunch of acetyl coenzyme A's can be converted into a fatty acid by a reaction that's the exact opposite of what we saw on the previous page. And acetyl coenzyme A is also easy to convert into a glycerol with the addition of another carbon atom. And then if I take 3 fatty acids plus glycerol, that will form a triglyceride. So if you eat nothing but sugar, because that glucose can be converted into acetyl coenzyme A, that acetyl coenzyme A can be converted into glycerol and into fatty acids, which will ultimately form a triglyceride, as we're starting to form down here. Let me show you just the acetyl coenzyme A. By looking at the molecular formula of this molecule, can you tell whether it came from a sugar or from fat? You can't, and neither can the body. This is why counting calories is important when it comes to maintaining body weight. not so much the type of food that you eat, but the number of calories that you get from said food. And that's because both sugars and fats can be broken down into this molecule here. So that's the beginning of the metabolism of fat. The metabolism of sugar was relatively simple. And in a lecture that's only going to last for an hour or so, I just considered all sugars the same. Glucose, fructose. I didn't talk about any of the differences in how we metabolize those, because they all get dumped into the Krebs cycle. Fats, on the other hand, are not so simple. I do have to discuss the difference between different types of fats. This is much more interesting when it comes to human health. This idea that not all fats were the same arose back in the 1970s. Back at this time, it was known that fat could cause deposits in our arteries, leading to high blood pressure and heart disease and an early death. And therefore, we thought that fats were bad. However, researchers studying Eskimos noticed that these Eskimos, or the Greenland Inuit, ate pretty much a high-fat, high-protein, low-carb diet. And yet they were much healthier than your average American. So if these Inuit were eating lots and lots of fat, why weren't they dying from heart disease the way that Americans were? And this led to the idea that maybe not all fats were the same. There might be good fat and bad fat. And therefore, the path to good health was to eat more of the good fats and avoid the bad fats. Had doctors and dietitians paid a little bit more attention, they might have noticed that these good fats that the Inuit were eating came from a type of animal. These were the omega-3 fatty acids and some other monounsaturated fatty acids that we're going to learn are good fats. The more of these that we get in our diet, the healthier we will be. However, instead, doctors and dietitians focused on the difference between animal fats and other types of fats. Saturated fats come from animals, and it was thought that these were bad. Still, we knew about this situation called the French paradox, and that is the French eat a whole lot of saturated fat. They also drink a lot of wine and smoke a lot of cigarettes compared to the British and the Americans, and yet they die from heart disease at much lower rates. So why is it that the French live longer and Americans and British do not, despite the fact that the French eat a lot of saturated fat? Well, obviously, speaking English must be bad for our health. And this, jokingly, was referred to as the French paradox. We thought saturated fats were bad, yet we still couldn't explain why the French were healthier than the British and Americans. In the 1990s, the Women's Health Initiative published a massive study looking at a huge number of women. And what they found was that women on a low-fat diet were not healthier or skinnier. And this was a pretty big shock. For decades, doctors and dietitians and other health gurus had been pushing the idea that fat was bad for you, especially saturated fat. And yet the WHI came back and said, nope, no, that's not the case. There were also a number of bits of data coming from the Harvard Nurses Health Study, which, depending on who you listen to, can be tweaked to say the exact opposite thing. So, lipid metabolism, what is good for us in terms of fat molecules, is complicated. So we need to go through that next. Let's start simple. This is a fatty acid. This is a fatty acid with no carbon-carbon double bonds. So every carbon has the maximum number of hydrogen atoms covalently linked to it. This is a saturated fatty acid. It is saturated with hydrogen atoms. If I were to magically strip away a couple of those hydrogen atoms, I would need to generate a carbon-carbon double bond so that every carbon atom has 4 bonds. Otherwise, they're going to be pretty unhappy. They just don't do that. This is now an unsaturated fatty acid. By being unsaturated, I mean I don't have the maximum number of hydrogens, and I have at least 1 carbon-carbon double bond. Please keep in mind when I say the maximum number of hydrogens, these hydrogens are covalently linked to the carbon atoms. This is not a hydrogen bond. That's the type of thing we see in water molecules, the interaction between a slight positive and a slight negative end of different water molecules. And that's a type of weak interaction. Here, we're only discussing strong covalent bonds. I could have a polyunsaturated fatty acid if I had more than 1 carbon-carbon double bond. But you absolutely must be clear on the difference between a saturated fatty acid, that's all single bonds, and an unsaturated fatty acid. That is any fatty acid with at least 1 carbon-carbon double bond. If you took your chemistry prerequisite, you might know that carbon-carbon double bonds come in different flavors. The 2 hydrogen atoms on either end of the double bond could be on the same side. This would be the cis conformation. Or the hydrogen atoms could be on opposite sides. This is known as the trans conformation. So a trans fat is an unsaturated fatty acid with a carbon-carbon double bond in the trans configuration, whereas other unsaturated fats are in the cis configuration. I don't know why we don't call them cis fats. We really should. And here is where chemistry meets physiology. Why do we care about this stuff? For starters, unsaturated fatty acids in the cis conformation have a kink in the molecule, and that means the molecules can't pack very tightly together because of this kink. If they can't pack tightly together, that means they're not going to be very dense, which in turn is going to make them more likely to be a liquid at body temperature. And liquid fats, otherwise known as oils, cannot lead to atherosclerosis. Liquids do not form plaques in our arteries. So that's one reason why cis fats are going to be healthy for us. They don't lead to plaque formation. What about that saturated fatty acid over there? It's more likely to be solid at body temperature, and that's one reason why people believe that saturated fatty acids are bad for you, but unsaturated fatty acids are good for you. In fact, this is why trans fats were touted as a healthier alternative to the animal fats, or saturated fats. And that was a mistake. Another mistake is thinking that cis unsaturated fatty acids are always healthy. Let me ask you this. If I take a bunch of healthy olive oil containing these monounsaturated fatty acids in the cis configuration and deep fry some chicken wings, is that going to be healthy for me? And the answer is no, of course not. Anything that's deep fried is bad for you, even if you start with healthy oils to begin with. And the reason is that just a little bit of temperature, enough that our stove is capable of generating this, can temporarily break that carbon-carbon double bond. But when we reform this bond, which we need to because we're not destroying matter nor creating matter, it's more likely to reform in the trans configuration. So on our stove, when I'm deep frying that chicken, starting with healthy olive oil, I am converting a bunch of those cis fatty acids into the trans configuration. And these molecules are more rigidly oriented in a straight line. Therefore, if I have multiples of these, they can pack tightly together. Trans fats, therefore, are denser than the cis fats, and therefore more likely to be solid at body temperature, which means these form plaques in our arteries, leading to high blood pressure, heart disease, and an early death. Deep frying anything is not healthy, no matter what you start with, whether it's a trans fat or a cis fat. It might have started off as an oil, but what's it going to be at the end of your frying? It's going to be a bunch of solid grease, stuff that's going to be difficult to remove from your frying pan or your pot. You're going to take a lot of soap to get rid of that stuff. You can't just wash it out and let it drain. On the other hand, if you are deep frying and you started with saturated fats, these are not going to change their conformation. They don't have any conformation. They only have carbon-carbon single bonds. Therefore, if you start with saturated fats, like lard, for instance, or coconut oil also has a lot of saturated fatty acids in it, you can't generate trans fats from this. A person's stove is just not capable of generating enough temperature to destroy covalent bonds and remove hydrogen atoms. To convert this saturated fatty acid into an unsaturated fat, I would have to remove hydrogen gas, and we just don't do that in the kitchen. Industrial processes can do this, but that's a different story. This saturated fatty acid might be healthier for frying things in than a healthy unsaturated fatty acid. And that's because the healthy unsaturated fatty acids can be converted into trans fats. That simply requires a change in the conformation of this bond, but that doesn't require the addition or subtraction of any atoms. That was two very important concepts. The difference between cis and trans, why one is healthy and the other unhealthy, as well as the difference between unsaturated and saturated, and why we can't consider unsaturated fatty acids as healthy. Trans fats are unsaturated. They are definitely not healthy, despite the fact that the food industry sold them as a healthy alternative to the saturated fats for decades. And doctors and dietitians went right along with it. It's not as simple or even as complicated as all of that, depending on how you look at it. I have to add one more layer of complexity. Unsaturated fatty acids can have a single carbon-carbon double bond, in which case they would be monounsaturated fatty acids, and we typically think of those as being good for us. Or they could have more than one carbon-carbon double bond. These would be polyunsaturated fatty acids. And we generally want to avoid the polyunsaturated ones. Here's why. It has to do with oxidation. Here is an unsaturated fatty acid in the cis conformation. A free radical, like this hydroxide ion, could strip a hydrogen atom, or just the proton, off of this fatty acid, leaving behind a negative charge. I now have a carbon atom that's only making 3 covalent bonds, so it's not very happy. But this negative charge could be shared between both carbon atoms on either side of the carbon-carbon double bond. So really, I've got two carbon atoms, each of which are 1/2 of a covalent bond short of being happy. That's not so bad. If I had multiple carbon-carbon double bonds, though, this negative charge here could be shared across all of the double bonds. This makes for a more stable ion, meaning it's more likely to be oxidized by a free radical in the human body. Let me say that a different way. Polyunsaturated fatty acids are more likely to be oxidized by free radicals in the human body, because when that happens, we generate a negative charge, but that charge can be shared across all of the double bonds. More double bonds means for a more stable ion. What's more is now this fatty acid that's a free radical could react with oxygen to form another free radical, one that could strip a proton off of another fatty acid. So this chemical reaction that we just did will happen again and happen again and happen again, as long as I have access to oxygen, which we always do, and as long as I always have access to fatty acids, which I always do. And especially if I have access to a lot of polyunsaturated fatty acids. So we want to avoid these in our diet. And this chemical reaction here, the generation of fatty acid free radicals, is going to be very important when I talk about good cholesterol versus bad cholesterol. Well, okay then. If those polyunsaturated fatty acids are going to be bad because they're more likely to be oxidized by free radicals, why don't I just get rid of those free radicals by eating antioxidants, and then I can eat whatever the heck fat I want to eat, right? Well, unfortunately, it's more complicated than that. And sure, we typically don't like oxidative reactions in the human body, at least not when they're happening to fatty acids or DNA. But this is one reason why saturated fats should not be considered bad fat. It's very difficult to oxidize a saturated fat. It has 0 carbon-carbon double bonds. It's the furthest away from a polyunsaturated fatty acid as we could possibly get and still be a fatty acid. Therefore, the more saturated fats that we have in our body, the less likely we are to have fatty acids oxidized in places that we'll talk about in a moment. This is one reason why we should not consider saturated fats bad for us. For decades, these were considered bad fat, and even today, saturated fats are called bad for human health in nutrition classes, in diet books, by your doctors, and all of these people are a little bit out of date. And one reason why they're out of date is these don't oxidize. And it's the oxidized forms that are really going to be bad for us. The physiology of how molecules behave in the human body can become very complicated, and I have not attempted to cover every aspect of fat metabolism. Nevertheless, some basic chemistry explains why there are good fats, bad fats, and those that are neither good nor bad. Trans fats are definitely bad for human health. It's very clear that eating more of these makes us less healthy and die sooner. That's because a trans fat, which is a type of unsaturated fatty acid, is held in a straight line because of the conformation of this carbon-carbon double bond. Therefore, these fatty acids are more likely to pack together tightly if they are in the human body, and therefore more likely to form a solid. And only solids can form plaques within our arteries, which leads to higher blood pressure and arteriosclerosis and heart disease. The cis fats were a different type of unsaturated fatty acid, and this kink that they are forced to bend into because of the conformation of their carbon-carbon double bond means that these cannot pack together as tightly. They are more likely to be liquids at body temperature, and liquids cannot form plaques. Therefore, these do not contribute to arteriosclerosis. In fact, these guys can help other fats to bend to fit their shape, to spoon to their conformation, if you will, hence making them more likely to be liquids as well. Saturated fats have no carbon-carbon double bonds. They could either be straight or they could be bendy. These are also more likely to be solids at body temperature, which is why some people get them confused with the trans fats. But we should not confuse the two. Trans fats have at least one carbon-carbon double bond. Saturated do not. And even though they have a higher melting temperature, and even though reducing the amount of these in our diet helps to reduce heart disease, what we see is that this doesn't make us live longer. And that's weird and really difficult to explain. In fact, not only can I not explain it in a 200-level anatomy course, I can't really explain it. And I don't think we have a good explanation for this. Nevertheless, what we see is that adding or subtracting saturated fats to our diet may change things in our body, but doesn't change how long we live. And therefore, we should not consider saturated fats as either good or bad. Back in the 70s and 80s, people were eating more of these, the trans fats, which we now know are really bad, in an effort to avoid these things, which really aren't all that bad. And this should be a little lesson for us in medicine. Anytime we think of trying to remove something from our diet, from the body, from wherever, we should ask, what's going to be replacing it? If it's really not that bad for us in the first place, we simply run the risk of increasing how many bad things that we expose ourselves to. I still haven't explained why the cis fats, like those monounsaturated fatty acids, are good for us. I did say they were more likely to be liquid at body temperature, and therefore wouldn't form plaques. But that really just explains why they aren't bad for us. One thing that makes them good is that they can't form inflammatory molecules like arachidonic acid and prostaglandins. Therefore, the more of these cis unsaturated fats that I have in my diet, the more of these I will have in my plasma membranes, and I will have fewer of the phospholipids with their two fatty acid tails that enzymes can use to generate inflammatory molecules like the prostaglandins. Hence, having more cis unsaturated fatty acids in the body tends to reduce inflammation. Now, inflammation is good to have in response to injury, but chronic inflammation is really bad for the human body. So these types of fats here can help to reduce chronic inflammatory responses, which in turn tends to increase our health and help us to live longer. And there are other reasons why the cis monounsaturated fatty acids are healthy for us. But really all that we care about is that they are healthy for us. And the data is very clear that the more of these that we get in our diet, if we lived more like the Inuit in Greenland rather than Americans or British, we would live longer. So we know that getting more of these from our food makes people live longer. Well, what if I want to eat crap and instead get these things in the form of a supplement? That's a lot easier. And in fact, the fish oil supplements are the #1 supplement in the United States. Unfortunately, the use of fish oil supplements does nothing for cardiovascular disease. We know that the molecules found in these supplements, when you get them in the form of fish or olive oil or some other food sources, definitely makes us healthier. But once you concentrate them into unnaturally highly concentrated levels in the form of pills, suddenly they're not healthy for us anymore. They don't help us in the way that fish and olive oil do, and in fact, these supplements increase our risk of colon cancer, in addition to not helping us with heart disease, and therefore, the science, at least today, would suggest that you can tell your patients to avoid these supplements. They're just not healthy for us, despite the fact that the supplement industry gets to say anything that they want. And they do. They suggest that these supplements will cure all sorts of diseases, despite the fact that there's just no evidence for that, and despite the fact that there's evidence that these supplements will do harm. To summarize, the omega-3 fatty acids, which were one type of cis monounsaturated fatty acid, was very good for human health. And the more of these that we got in our diet, the healthier that we would be. For instance, adopting a Mediterranean diet is very healthy. This contains a lot of fish and olives and other sources of these types of good fats. Eating more fiber and whole grains is also beneficial for other reasons. And again, the evidence would suggest that a healthy diet should include as much of these as possible. On the other hand, we should definitely avoid this type of unsaturated fatty acid, the trans fats. And we should also avoid the polyunsaturated fatty acids, because they are more likely to become oxidized. We also have good evidence that too much sugar is bad for human health, and we'll talk about that in the second half of the lecture. What's pretty important to understand, though, is that there's no evidence either way on the saturated fats. These are neither good nor bad for us. If you're going to deep fry, I would definitely suggest using the saturated fats, because these can't be converted into the trans fats. They're not going to be healthy for you, but at least they can't be converted into something that's unhealthy. And we also don't have any evidence to suggest that fat from animals, like meat or eggs, is going to be particularly good or bad for us. It seems to be fairly neutral. Those were the different types of fatty acids, and I focused heavily on their chemical differences, which tells us a lot about how they behave in the human body. If you focus on any one particular detail of their physiology, it can be a lot more complicated than I have presented here. I focused on the overall mortality data, which gives us a big picture of whether these chemicals are good for the human body, bad for the human body, or neither. The cis unsaturated fatty acids seemed to be good because they were liquid at body temperature, which meant they were not only not going to cause atherosclerosis, but could help other fats become liquid as well. They also reduced inflammation. The trans fats, on the other hand, tended to be solid at body temperature, and that allowed them to form plaques within our arteries. The unsaturated fatty acids, on the other hand, did not have any carbon-carbon double bonds. And even though they could also be solid at body temperature, they had no effects on overall mortality. They didn't seem to cause people to die earlier or later. Any one of those could become a part of a triglyceride, which is how we store fat in the human body. That was 3 fatty acids plus a glycerol molecule. Next, we must consider how fatty acids and other lipids are transported through the human body. Because they are not water-soluble, they cannot dissolve in blood plasma, and instead must be transported by some form of lipoprotein. This is going to be our next topic, the movement of lipids via HDLs and LDLs. A few fatty acids may be found floating through the bloodstream. We don't want too many of these because they're likely to stick to the arterial walls rather than stay dissolved in the blood plasma. Most of our other lipophilic molecules will be transported in one form of a lipoprotein. We're going to need a protein coat to allow these lipids to be transported through the bloodstream. Free fatty acids are individual fatty acids found floating in the bloodstream, usually bound to the serum protein albumin. Too many of these can increase the risk of arteriosclerosis because they don't like remaining dissolved in plasma and would prefer to stick to a more lipophilic wall of arteries. Nevertheless, they are a very important energy source. Muscle tissue, especially cardiac muscle tissue, prefers burning fatty acids whenever possible. The vast majority of fatty acids are transported within a lipoprotein, in addition to another very important lipid, cholesterol. The fatty acids in cholesterol make up the core component, which is surrounded by a bunch of amphipathic proteins, the lipophilic portion facing the fatty core and the water-soluble portion facing the bloodstream. This means that the lipoprotein is completely surrounded with a water-soluble shell and hence can dissolve in blood plasma for transport throughout the body. There are a number of different types of lipoproteins. Here are the 5 that are usually listed in anatomy textbooks, although we are learning that there are many different types of LDLs and HDLs, so we could make this list even bigger if we wanted to. I'm going to keep things fairly simple. We're going to simplify things and discuss HDLs versus LDLs. These stand for high density and low density lipoproteins. This is their first major difference. The high density lipoproteins tend to have less fat and cholesterol. This is one reason why we typically think of these as good cholesterol. The LDLs, on the other hand, are much larger, and these typically have more fatty acids and cholesterol. And this is one reason why we typically think of these as bad. This is not a very good reason, because fats, after all, are very important for the human body, and cholesterol is absolutely necessary as well. The molecule cholesterol is synthesized in the liver and is converted into many other things throughout the body. Hence, it needs to be transported to other places to form steroid hormones, vitamin D, and to become a part of the plasma membranes of all cells. Hence, it's very important that we transport enough cholesterol to these places and do so safely. The lipid, therefore, synthesizes the proteins that make up a low-density lipoprotein. It also synthesizes cholesterol, and it can package some fatty acids from our diet into these LDLs for transport to other tissues in the human body. If we have excess fat or cholesterol, this can be transported to adipose tissue for long-term storage. This is perhaps a better reason for thinking of LDLs as bad cholesterol. It's a sign that the body has excess amounts of cholesterol and fat and is putting on adipose tissue, which most people don't need more of. Another very important type of lipoprotein were the chylomicrons that we discussed in the previous chapter. To absorb fat and cholesterol from our diet, it must be first coated by the epithelial cells of the intestines into another type of lipoprotein, the chylomicron. These macromolecules are way too large to diffuse into capillaries, and therefore can only enter through the mini valves of our lymphatic system. Specifically, we call these lymphatic vessels in the intestines the lacteals, and these are responsible for absorbing fat and cholesterol and transporting it, ultimately, to the bloodstream. In addition to the LDLs, which were made by the liver for transport to the body, HDLs are synthesized in peripheral tissues to be sent back to the liver for excretion. This is one reason why we think of HDLs as good cholesterol. This is a sign that the body is removing excess fat and cholesterol, and this should help reduce the risk of arteriosclerosis. When HDLs reach the liver, they can bind to HDL receptors found on hepatocytes, transported into these cells, and then converted into bile and excreted from the human body. Fat and cholesterol that's no longer in the body cannot form atherosclerotic plaques. More importantly, as an HDL is traveling to the liver, it can bump into fatty plaques along the way and scavenge fatty acids from them, hence cleaning the blood as it travels back towards the liver. This is another very good reason for thinking of HDLs as good cholesterol. To call LDLs bad cholesterol is an oversimplification. They aren't by their nature bad. In fact, they serve an absolutely necessary function in the human body, the transport of fatty acids and cholesterol from the liver to our peripheral tissues. We can't live without that. They can, however, become a problem along the way. LDLs, to get to these peripheral tissues, must exit the bloodstream, traveling between endothelial cells and through the connective tissue of our artery walls. It's here that they can become trapped. This still isn't a problem. That's just a bunch of fat and cholesterol amongst the collagen fibers of my artery walls. If these LDLs contain a high number of polyunsaturated fatty acids, this is where things can be a problem. These types of fatty acids can be easily oxidized by free radicals. That's still not a problem yet. The problem comes when white blood cells are attracted to these free radicals, triggering chronic inflammation. This will lead to the overproduction of collagen fibers here in the connective tissue. These collagen fibers can come from the endothelial cells, which is weird for an epithelium, as well as nearby fibroblasts. And this leads to hardening of the artery wall, which will increase blood pressure, which can increase the risk of heart disease and early death. So the way that LDLs actually became bad was a multi-step process and involved not just the LDLs, but the polyunsaturated fatty acids as well. And an LDL, being larger than an HDL, will probably have more polyunsaturated fatty acids within it, making LDLs bad cholesterol. Another reason why HDLs can be considered good cholesterol is that they're smaller and therefore less likely to get trapped within the connective tissue of our artery walls. And where they exit the body is special. The capillaries in the liver are sinusoids and leave gaps between the endothelial cells, making it easy for these HDLs to exit the bloodstream and travel to a hepatocyte. For this reason, HDLs typically do not get trapped within our artery walls and hence do not lead to arteriosclerosis. Another reason to consider these good cholesterol. This will bring us back to the topic of antioxidants. If there wasn't anything inherently bad about an LDL, just the fact that the polyunsaturated fatty acids within it could become oxidized and attract white blood cells, triggering inflammation, what if we stopped that oxidation reaction by eating a bunch of antioxidants? That could reduce the oxidation of polyunsaturated fatty acids, lowering foam cell production and reducing inflammation within our artery walls. Unfortunately, nitric oxide, which is our body's prime vasodilator, is also a free radical. So even though antioxidants could have this benefit here, they might just as well destroy nitric oxide, reducing vasodilation signals. And with less vasodilation will come higher blood pressure, which will increase the risk of heart disease. So the effects of antioxidants are complicated. Luckily for us, foods that are rich in antioxidants don't have enough of these chemicals to where we really see either one of these happening to any significant amount. What I'm talking about here is probably what happens after somebody takes antioxidants in an unnatural dose found in supplements. Here's my summary slide. The HDLs are synthesized in the peripheral tissues and are sent back to the liver for excretion, whereas the LDLs are made in the liver and are sent to peripheral tissues for storage. That will include fats like fatty acids and triglycerides, as well as cholesterol, which can be synthesized in the liver. Along the way, if these LDLs get trapped in our artery walls, that can increase the risk of atherosclerosis and heart disease. In this chapter and the previous chapter, we have covered a number of very important functions of the liver. In the previous chapter, we learned that the P450 enzymes could detox chemicals found within the bloodstream. The liver can also store excess nutrients in the form of glycogen and fat. The liver converts ammonia into urea, which we will see in the next section is very important. It also makes a number of important plasma proteins like albumin, and it's responsible for packaging up fatty acids into those LDLs for transport to the peripheral tissues and for the removal of fatty acids found in HDLs coming from peripheral tissues. The new task that we just added was the synthesis of cholesterol, which the liver does at a constant level. Therefore, reducing cholesterol in our diet is not always an effective way at reducing cholesterol in the body. Our diet can regulate the speed at which the liver synthesizes cholesterol. For instance, eating the cis fats tends to lower cholesterol production, whereas trans fats tends to increase cholesterol production. But this is not the reason that we considered cis versus trans, healthy versus unhealthy. There were much more direct ways that the trans fats were bad for human health and the cis fats were good for human health. And that's because the role of cholesterol is complicated. Cholesterol, once again, is not a bad molecule as long as it's in the right place at the right time. Nevertheless, some of your patients will have livers that produce excessive levels of cholesterol. And for these people, we can give them medications which reduce the production of cholesterol by the liver in the form of drugs called statins. This pathway over here to the right shows how the liver can start with acetyl coenzyme A and go through all of these different steps to ultimately produce a lipophilic molecule, cholesterol. Each one of these arrows is catalyzed by an enzyme that can be inhibited by certain drugs. We certainly can't reduce acetyl coenzyme A levels by any sort of dietary choice other than starvation. Therefore, we can't really stop the liver from producing cholesterol without inhibiting some of these enzymes here. Statins are a large family of drugs which can lower LDL levels. And lower levels of LDLs are correlated with a longer life and lower chances of dying from heart disease. I'll come back to what this word correlated means, but it's a very significant word. I'm going to go through this research article over here with a quick caveat. When it came out, it was quite a shock, and we know a little bit more about statins now. But when this came out, it suggested that if you gave statins to 100 people, all 100 of them saw lower levels of LDLs. But for 97 of them, that did not lead to a longer lifespan or a reduced risk of heart disease. Only one person out of that 100 got that benefit. Now that may seem like that's not very good, but because we give these drugs to so many patients, that's probably saving 50,000 lives per year in the United States. That's a significant number of heart attacks that are delayed or avoided. Unfortunately, in these studies, 2 out of 100 people were dying earlier due to complications such as diabetes. And the benefit that this one person got here seemed to be wiped out by the detriment that these 2 people got here. So when we averaged everything out, there was no reduction in total mortality. Now, this was a big deal when it came out, and what it really suggests is we shouldn't just give statins to everybody. This led to changes in how we prescribe these medications, and we're a little bit better at identifying who might actually benefit from these drugs and who should probably avoid these medications and try some other way to lower their blood pressure. One of the results was that statins can reduce the risk of having a heart attack by 50%. We went from here in the control group down to here in the statin group. That was a measurement of the relative risk. For instance, if this group had a 2% chance of dying and we went down to 1%, that's a 50% reduction in the risk of dying from heart disease. Another way of illustrating that would be to say there's a 1% reduction. Going from 2% down to 1% is only a 1% change. That's the change in the absolute risk. So which one of these two is correct? Well, they're actually both correct. You could say it either way. You just have to tell people which way it is that you're saying, whether it's relative or absolute risk. And I suppose you'd probably want to choose this one over here if you were trying to sell these drugs. But you might want to choose this one over here if you're trying to make these drugs look ineffective. In addition to cholesterol and fatty acids, the other component of these lipoproteins were proteins. Here are 2 examples of some of those proteins that would be the outer coat of an HDL or an LDL. When this one here is mutated, that can lead to problems forming HDLs, meaning the body can't remove fat and cholesterol as easily, and this can lead to hyperlipidemia. Conversely, a mutation in the receptor for LDLs means that these proteins tend to stay in the bloodstream, which can lead to elevated levels of cholesterol found within the blood. Both of these are genetic conditions that can be passed down in families, leading to problems with blood lipids that we might want to treat with a drug like a statin. Another factor that you will have to consider in your patients are vitamin D levels. Low levels of vitamin D can lead to an increase in the production of LDLs by the liver. This is a homeostatic feedback mechanism. Vitamin D is synthesized from cholesterol. So if we have low levels of this compound, we can send more cholesterol to the skin, and to do so we have to package it up into LDLs, and hopefully this will compensate for the lower levels of vitamin D by increasing vitamin D production. Another mutation that can lead to problems with LDLs is the APO4E allele. Many people of European and Asian descent have this allele, which can increase levels of cholesterol, and this can increase the risk of Alzheimer's disease and cardiovascular disease. On the other hand, it protects us from vitamin D deficiencies. In this day and age, that's really not the best trade-off. We can get ample vitamin D from sunlight and from nutrition. But 10,000 years ago, this must have been a pretty good trade-off for those of us who come from places where sunlight isn't 24/7. Other factors can affect HDL and LDL levels. Exercise is a big one. Aerobic exercise tends to decrease LDLs while increasing HDLs. Statins and niacin can also decrease LDL levels. Conversely, stress, cigarette smoking, coffee drinking, and saturated fat intake can all increase LDL levels. So for some of us, we might be a little bit worried about a couple of these. Does that mean we really need to stop drinking coffee and eating saturated fat? Well, let's not forget about the French paradox. The French eat a lot of saturated fat and drink a lot of coffee, and yet they don't die from heart disease nearly as much as Americans. So how can we explain this here? If saturated fat and coffee drinking increases LDLs, and we think of LDLs as bad, why aren't these things necessarily bad for us? And hopefully you already understand that LDLs aren't inherently bad. But this is also a problem of correlation versus causation. High LDLs and low HDLs are correlated with poor health and an increased risk of atherosclerosis. Conversely, low LDLs and high HDLs are correlated with a reduced risk of atherosclerosis and dying from a heart attack. However, simply raising HDLs or lowering LDLs might not make us healthy. For instance, a couple of drug companies had chemicals which could raise HDLs, but these were stopped in phase 2 trials because they were ineffective at making people healthy. They raised HDLs just fine, but that didn't make people any healthier. Therefore, not everything that lowers LDLs or raises HDLs is actually going to be beneficial to human health. And this brings me to this topic here, the difference between correlation and causation. Let's focus on exercise. We absolutely know that exercise is good for human health. There's no argument about that. But why is it good for human health? Well, one possibility is that exercise leads to lower LDLs. We know that happens. And this could lead to a reduction in atherosclerosis, which could make us live longer by protecting the heart. But another hypothesis is that exercise could lower LDLs as well as do other things that are good for human health, like promoting angiogenesis and increasing the strength of our heart, which would reduce the speed at which the heart needs to beat to pump oxygen efficiently. These two things could be what causes us to live longer when we exercise, and LDLs are simply correlated with this. We see that in people who exercise, they live longer, but it might not be because their LDLs are lower. That might just also be happening. We didn't have to worry about correlation versus causation when we discussed good fats versus bad fats. The monounsaturated cis fatty acids were definitely good for us. Higher levels of those in our diet has proven health benefits. Conversely, trans fats are absolutely bad for human health. Those should be ingested in very moderate or no levels whatsoever. Saturated fats, on the other hand, seem to be neither good nor bad. What was bad was what we did when we removed saturated fats from our diet. Back in the 70s and 80s, we typically replaced the saturated fats with the trans fats, and that was definitely not good for human health. And then later, when we found out that the trans fats were bad, the saturated fats were replaced with extra sugar. And as we'll see in the second section of this lecture, that's also not good for human health. On the other hand, when it came to HDLs and LDLs, we did call these good cholesterol and bad cholesterol. But this was a lot more complicated. LDLs weren't bad by nature. In fact, they serve an absolutely necessary function in the human body. We must be able to transport the cholesterol that is synthesized in the liver as well as additional fatty acids that we get from our diet, to other tissues in the human body. Otherwise, we can't make hormones or have functional plasma membranes. The reason that LDLs could be bad is that they could get trapped as they exited the bloodstream, and that would then lead them to be able to be oxidized by free radicals, which could attract white blood cells, which would turn into foam cells, which triggered inflammation that could lead to atherosclerosis. So the reason that LDLs could be bad was a multi-step process. On the other hand, HDLs we typically think of as good because they can scavenge fat from plaques and transport this to the liver for excretion from the human body. As we saw, though, simply elevating HDL levels didn't necessarily make people healthier, and simply lowering LDL levels doesn't make everybody healthier either. But this would be a good spot to take a break. Go grab a snack with nuts or olives in it, and then come back and we can go over the second portion of this chapter. Welcome back. In this second section, I'll talk about the word essential, which can mean necessary, but it has other meanings as well. We'll talk quite a bit about diabetes and the differences between type 1 and type 2 diabetes. We'll then move on to talk about vitamins and whether or not they are good for us. They absolutely are. We need a certain amount in our diet or we'll get sick and die. But what about twice as much or 10 times as much? Does that make us even healthier? And I'll return to this topic of antioxidants. And lastly will be a very brief overview of the complexities of hunger. I'm going to start with protein metabolism and how we can break down amino acids to be used as energy. We'll then move on to discuss the absorptive and postabsorptive state and discuss some very important hormones, insulin and glucagon. I'll also cover the difference between ketosis and ketoacidosis. Lastly, we'll talk about some other topics in nutrition and metabolism. Let's start with proteins. The body synthesizes 100,000 or so proteins, all from the same 20 amino acids. All tissues must get these amino acids from the bloodstream and convert them into proteins by linking them with peptide bonds. This is, of course, translation of mRNA inside of cells. This is an anabolic reaction. We frequently, however, eat more amino acids than we need, so it is possible to break them down to generate ATP. Not all amino acids are going to enter the Krebs cycle at the same point, but once again, we're going to see some similarity between amino acid metabolism and carbohydrate and lipid metabolism. When we have excessive levels of protein in the diet, the amino acids from these proteins can be used for energy. This is especially important when glucose and lipids are not in adequate supply. We will have to rely on breaking down proteins for fuel. To do this, we must first get rid of these guys over here, the ammonia group. That's because the nitrogen atom was not represented at all when we were discussing the Krebs cycle. So this is not going to fit into any of the enzymes that we use to break down molecules for energy. There are two basic ways to get rid of this nitrogen atom. I can either shift it to another molecule, that's called transamination, and that can be used to generate different amino acids. To completely remove this nitrogen atom requires a process called deamination, and we will wind up with an ammonium molecule as a waste product. Transamination is important for synthesizing non-essential amino acids, whereas deamination is what we do when we're breaking down amino acids for fuel. Keep in mind that when we were talking about the Krebs cycle and lipid metabolism, we were only dealing with 3 types of atoms: carbon, oxygen, and hydrogen. Amino acids have at least 1 nitrogen atom, possibly more depending on which R group there is. Therefore, to convert this amino acid into something that my mitochondria can use, I have to remove the nitrogen atoms. And I have enzymes that can do that. And this should leave me with 2 or 3 carbon compounds, such as pyruvic acid, or, as shown here, acetic acid, which of course could attach to coenzyme A and then directly enter the Krebs cycle to be broken down further and generate ATP in the process. We now have a third way in which tissues can generate ATP. Glycogen from the liver could be broken down into individual glucose molecules, which are dumped into the bloodstream and travel to target tissues for usage. As we'll see, glucose will have its issues when traveling through the bloodstream. Fatty acids can also leave the liver in the form of an LDL to travel to target tissues for usage. And now, proteins can be broken down into amino acids. This will generate keto acids, like this pyruvic acid that we see here. Fatty acids can also be broken down into keto acids and dumped into the bloodstream. We frequently call these glucose equivalents. These keto acids are acids, but luckily my blood buffering systems should keep these from altering the pH of my bloodstream as they travel from the liver to my target tissues to be burned for fuel. If I don't have enough sugar, however, my body may have to break down more fatty acids and more proteins, in which case I will be dumping more keto acids into the bloodstream, and it's possible for these to overwhelm the buffering systems. At this point, some of these keto acids would be converted into ketone bodies, like this molecule of acetone that I have shown here, and this could lower the pH of the bloodstream, causing ketoacidosis. The production of keto acids is something that the body does every day and has great benefits. For instance, burning fat for fuel will require the generation of keto acid intermediates to be dumped into the Krebs cycle. But as long as this is happening in a controlled amount, those fatty acids can easily travel to the target tissues via the formation of LDLs, and then the keto acids are only produced within the mitochondria. And it's safe to produce keto acids there. Mitochondria are acidic. We typically see ketoacidosis only in extreme conditions, such as uncontrolled diabetes and starvation, where the body has to break down so many proteins and fatty acids that we don't have enough LDLs and buffering systems to carry them to our tissues adequately, and more keto acids then wind up in the bloodstream than we can handle. One of the signs that this is occurring is a sweetness of the breath or sweat, because some of those keto acids will be further converted into ketone bodies like acetone, which evaporate very quickly. The body can break down excess amino acids for energy. Some amino acids will be broken down in the liver to generate keto acids, and thanks to the blood buffering systems, this should not alter the pH as they travel to target tissues. But because the buffering systems do have limits, the body typically does not rely on protein catabolism when it has the capability to break down sugars and fats for fuels instead. Another reason the body does not prefer to rely on protein catabolism is the generation of ammonium ions. These are toxic. For the same reason that you would not want to drink ammonia, the body does not want to produce these ammonium ions. So when it does, it must quickly neutralize them. And we typically only do this in one target tissue, the liver. The liver can use carbon dioxide to quickly neutralize these ammonium ions to generate a much more stable molecule of urea and another one of water. The body can't use this urea for anything, but at least it will not react with other molecules and can be safely dumped into the bloodstream to travel to the kidneys for filtration and excretion from the human body. But those are two reasons why the body prefers to burn fat and carbs for fuel rather than protein. We don't want to overwhelm the buffering system by generating too many keto acids, and those ammonium ions can do damage in the short time that they exist before they are neutralized. Out of the 20 amino acids that the body uses, some of them can be converted from one another. These are known as the non-essential amino acids. For instance, elevated levels of alanine through the process of transamination might be converted into more cysteine or more glutamate if we didn't happen to get these in our diet. The essential amino acids are those that the body cannot produce on its own. These must be ingested from our diet, and that is what the word essential means here. We must get them from a fruit or vegetable source, from the essence of another organism. This word essential therefore has two meanings. It can mean necessary or containing the essence of a plant or other organism. It can be used to confuse people. For instance, many essential oils are things that you would not want to eat because they're poisonous. They are essential because they were extracted from a plant source. Here's my big summary slide. To generate energy from a protein source, we must first break those proteins down into amino acids. We must remove any of the nitrogen atoms by the process of deamination, but then I should wind up with a keto acid, such as acetyl coenzyme A, which could be broken down and some of the energy that's released trapped in the form of ATP. Excessive amounts of acetyl coenzyme A, however, could be used to form fatty acids and glycerol, which could then be converted into a triglyceride for storage in our adipose tissue. The same thing can happen with carbohydrates being broken down into glucose. That could be used to generate ATP, or excessive levels of glucose could be converted into fatty acids and glycerol to be stored in our adipose tissue as a triglyceride molecule. Later, those triglycerides could travel to my target tissues in some form of lipoprotein, be broken down into glycerol and fatty acids, which could then be further broken down into acetyl coenzyme A to be used for energy. That wraps up protein anabolism, or the conversion of non-essential amino acids to other non-essential amino acids. The essential ones we had to get from our diet. We talked about catabolic reactions, such as deamination, which could generate this waste product, urea. It would also generate a keto acid that I could use for energy. Luckily, we get to skip over nucleic acids. Those are only good for generating DNA and RNA molecules. We don't break them down for energy or convert them into fat for storage. So we now get to move on to bigger issues. I'll talk about some of these metabolic tissues. The liver has been central in regulating the body's metabolism. It can store excess nutrients for a later time and release them into the bloodstream as needed. Adipose tissue was also good at storing excess nutrients. Only one type of nutrient, though, triglyceride molecules. Skeletal muscle tissue could store glycogen, which could also be released back into the bloodstream in the form of glucose if needed. It also contains a large number of proteins, which could be broken down in times of starvation. That would generate keto acids in the blood. Neural tissue cannot store any of its own energy. It has no adipose or glycogen reserves. Therefore, it's important that an adequate amount of nutrients be available in the bloodstream at all times, even in between meals, to make sure that our neural tissue continues to function. And then there's every other part of the body, which needs nutrients as well, for ATP and for building new cells and whatnot. The metabolic activities of the human body can be broken down into an absorptive state and a postabsorptive state. The absorptive state happens right after a meal, when nutrients are being absorbed into the bloodstream from the digestive tract and are therefore in high quantity. The major job of the body at this time is to use what nutrients it needs and store the rest for later. The primary hormone that regulates these processes is the hormone insulin, which comes from the pancreas. Later, during the post-absorptive state, nutrients in the blood may drop, and so the major metabolic activities will revolve around breaking down larger macromolecules into smaller ones that can be dumped into the bloodstream for use by the body's tissues, especially the brain, which has no energy reserves of its own. The primary hormone regulating these processes is glucagon, which also comes from the pancreas. During the absorptive state, most tissues will be using glucose for fuel. That's both because glucose levels in the blood should be high, and because the breakdown of glucose is relatively biochemically simple. There are some tissues, like skeletal and cardiac muscle, that will still prefer to burn fatty acids. All of our other nutrients will be converted into larger molecules for storage. Muscle tissue can convert amino acids into proteins, like actin and myosin, and convert glucose into glycogen. The liver, similarly, can convert amino acids into proteins, and it can convert glucose into glycogen or into fat for storage. Adipose tissue can convert glucose and fatty acids into triglycerides for storage. All other tissues have minimal energy reserves, and therefore will simply use whatever nutrients they need at this time. Insulin is the prime regulator of those processes. The secretion of insulin from the pancreas is stimulated by high blood glucose levels, high blood amino acid levels, and increased levels of certain hormones made by the duodenum, such as GLP-1, gastrin, CCK, and secretin. Insulin affects nearly every cell in the human body. From the neck down, its main effects are to signal the movement of glucose and amino acids out of the bloodstream and into target tissues. This is one reason why bodybuilders will purchase insulin on the black market, to increase the amount of amino acids that enter into muscle tissue to be converted into proteins like actin and myosin, which increases muscle size and strength. It's important to remember that insulin, being a hormone, is just a signal. It does not bind to glucose and do anything directly. When blood glucose levels rise, the beta islet cells of the pancreas can detect this elevated glucose. These are the only cells that we are discussing that can actually monitor blood glucose levels. In response to elevated blood glucose, this will trigger the release of insulin into the bloodstream, which will travel throughout the body, binding to insulin receptors, which are found on most target tissues. This will activate a second messenger pathway, which can do a number of things. It will drive the movement of vesicles to the plasma membrane, moving glucose transporters to the place where they can move glucose from the blood into the cell. If we were to increase cytoplasmic levels of glucose, it might diffuse back outwards again. So to prevent this from happening, We also activate enzymes which can begin the metabolism of glucose, or at the very least phosphorylate it, making it much more hydrophilic and therefore less likely to diffuse back out of the cell. This can trap that glucose in the cell. We then either burn that glucose for fuel or begin converting it into some sort of macromolecule. Which macromolecule we build it into depends on what type of cell we're discussing. On the previous slide, we said adipocytes would convert glucose into triglycerides, whereas skeletal muscle tissue would convert it into glycogen. I try not to repeat myself in these videos, but I'm going to do so now. Insulin is a hormone and therefore just a signal. It will activate cells to do something with blood glucose, namely transporting it into the cell, out of the bloodstream, and either using it for energy or converting it into a macromolecule for storage. If insulin cannot do its job for any reason, this will lead to the condition diabetes mellitus, of which there are two major types, type 1 and type 2. Type 1 diabetes is caused by inadequate insulin production, whereas type 2 diabetes is caused by inadequate insulin receptor function. Either way leads to low levels of insulin signaling. That's the important concept here. And when we don't have enough insulin signaling, too little glucose will be leaving the bloodstream, entering our cells for use in metabolism. And this elevated glucose in the blood will also cause damage to certain tissues in the body. Type 1 diabetes is an autoimmune disease. It's caused when the immune system attacks the beta islet cells of the pancreas, reducing its ability to produce insulin when blood glucose levels rise. This was formerly called juvenile diabetes because this condition commonly starts early in childhood. The treatment of this disease is conceptually simple. We can simply replace the insulin that is needed through injections or pumps. On the other hand, type 2 diabetes is caused by a deficiency in insulin receptors. This is often caused by excessive levels of insulin in the bloodstream over long periods of time, and therefore the best treatments usually do not involve insulin injections. However, insulin injections are one of the most common treatments for type 2 diabetes, so I need to explain that contradiction here in a moment. Type 2 diabetes, or adult onset diabetes, is the most common form of diabetes in the United States and other countries, and involves a disruption in our homeostatic controls of hormone levels. To help illustrate the primary cause of type 2 diabetes, I have a number of target cells here with insulin receptors. One of our biggest risk factors for type 2 diabetes is obesity, and obesity can often be caused by a high glycemic diet. It's the high glycemic diet that's important here. If too much sugar is constantly being absorbed into the blood, the pancreas will be constantly secreting insulin, which will bind to insulin receptors, and this should lead to a reduction in blood glucose. But with chronic insulin signaling, this will activate a negative feedback mechanism, which reduces the number of insulin receptors. It doesn't have to go down to zero to lead to a significant reduction in insulin signaling. At this point, the cells would no longer be removing glucose from the bloodstream, which will lead to elevated blood glucose levels, as well as cells that do not have enough glucose for energy. They will then have to rely on burning proteins and fatty acids for fuel. Insulin injections can be used to try and make sure that what few insulin receptors are left are working at peak capacity to try and help lower blood glucose levels. Because this disease was caused by high levels of insulin in the first place, increasing insulin levels will only make this disease progressively worse. So why would we ever prescribe insulin injections to people with type 2 diabetes? The answer to that is that we're weighing risk versus reward. The risks of allowing elevated blood glucose levels to stay there are not worth the risks of making this disease worse. The summary, though, so far is that type 1 diabetes is caused by inadequate insulin production, whereas type 2 diabetes is caused by inadequate insulin function, usually due to the reduction in insulin receptors. Both diseases are characterized and in fact defined by elevated blood glucose. The causes are what are different. The body likes burning sugar for fuel, and yet too much glucose in the bloodstream has dangers. For one, elevated blood glucose levels, seen with type 2 diabetes, can lead to too much glucose winding up in the filtrate of our nephrons. It might exceed the transport maximum in the proximal convoluted tubule and then wind up in the more distal portions of the nephron, where it acts as an osmotic diuretic. This will draw water out of the bloodstream, becoming urine, which can lead to dehydration. Excess urine production is accompanied with glucose in the urine, which is how we might diagnose the disease. It's the dehydration, however, that we worry about. Lower levels of water in the brain, for instance, can increase sodium concentrations in the extracellular fluid, and this can mess with ion gradients, disrupting action potentials, leading to altered neural function. For people with diabetes, if they go into a state of hyperglycemia because they are not regulating their disease properly, this can lead to behaviors that appear to be associated with excess alcohol intake, but are in fact due to excess blood sugar. Glucose is also sticky, and it can stick to arterial walls and red blood cells, leading to atherosclerosis. This can damage some of the very fine capillaries found within the kidneys, the glomerulus, for instance, leading to kidney damage. It can also damage the fine capillaries of the eyes, leading to progressive blindness, and it can also lead to damage to the capillaries feeding the tissues of our extremities, which can lead to gangrene and may ultimately require amputation of the toes or feet. On the other side of this page is a condition called hypoglycemia. This is not something that people with diabetes would normally experience. Hyperglycemia is the condition caused by the disease. Hypoglycemia is iatrogenic. It is a condition that can be caused by the medicine. In this case, too much insulin. For instance, a patient with diabetes may inject themselves with insulin a little bit too late. After they then experience hyperglycemia, they may forget that they've injected themselves with insulin and inject themselves again. Now suddenly their body has a double dose of insulin, which can cause blood glucose levels to drop well below the homeostatic set point. This can cause the brain to stop functioning, leading to shock, coma, or even death. The treatment for hypoglycemia is relatively simple. Administer carbohydrates in a form that can be quickly absorbed, such as fruit juice. The treatment for hyperglycemia would be injecting insulin, but this is not something that is typically done by anyone other than the patient or by highly trained professionals. You would not inject somebody who you suspect is suffering from hyperglycemia with their own insulin for fear of sending them into a state of hypoglycemia because you got the dosage wrong. To summarize, type 1 diabetes, or insulin-deficient diabetes, is caused when the pancreas cannot produce insulin in adequate supply. This can be treated with insulin injections. This insulin injected into the bloodstream can help to reduce blood glucose levels and keep the disease under control. On the other hand, type 2 diabetes, or insulin-resistant diabetes, is caused by too much insulin. This will lead to a reduction in the insulin receptors, which in turn leads to a reduction in insulin signaling, for a different reason than type 1 diabetes, but we get the same results. Glucose cannot leave the bloodstream, and this therefore can lead to hyperglycemia. On the other hand, during the postabsorptive state, the body is primarily undergoing catabolic reactions to dump glucose or glucose equivalents into the bloodstream so that the brain and other tissues have adequate supplies of energy. During the postabsorptive state, muscle tissue can break down glycogen into glucose and dump this into the bloodstream. It can also break down protein into glucose equivalents, such as pyruvic acid and acetic acid, which would also enter the bloodstream and could be used by target tissues for energy, such as the nervous system. The liver can also break down glycogen into glucose. Both the liver and adipose tissue can also mobilize energy reserves from triglycerides. The liver could move fatty acids through the body in the form of LDLs. Otherwise, triglycerides must be broken down into fatty acids that enter the bloodstream directly to become free fatty acids, or they must be broken down into glucose equivalents, such as pyruvic acid and acetic acid once again. We do a lot of this because we don't want too many free fatty acids in the blood, and in fact, we can't get many free fatty acids in the bloodstream because they're lipophilic. These glucose equivalents, however, are water soluble and can therefore travel readily to target tissues like the brain from our adipose or liver tissue. Glucagon is the hormone made by the pancreas that regulates these processes. It is the mirror hormone of insulin, meaning it does the exact opposite of insulin and should not be found in the bloodstream at the same time as insulin. Epinephrine can also assist glucagon. This will activate the liver, muscle, and adipose tissue to mobilize nutrients for usage. It helps to promote fat breakdown and glycogenolysis. To summarize, the absorptive state was primarily regulated by insulin, where the main job was to move glucose, amino acids, or maybe some other nutrients out of the blood and into target tissues. And whatever was in excess of their energy needs would be converted into a larger molecule for storage, primarily glycogen or triglycerides. During the post-absorptive state, glucagon was dumped into the bloodstream, and this triggered target tissues to break down larger molecules into smaller ones, releasing glucose or glucose equivalents into the bloodstream for use by other tissues. The opposing effects of insulin and glucagon were similar to the opposing effects of the mirror hormones PTH and calcitonin that we covered in BI 231. And just like you may have done then, if you learn how insulin works, then all you need to know is that glucagon does the exact opposite. Next, I'm going to move on to nitrogen balance. To make proteins from the 20 amino acids that we need, I need to have all 20 of those amino acids. Some of them I can convert from other amino acids. Those were the non-essential amino acids. But to get the essential amino acids meant I had to get those from my diet. When eating meat, meat is referred to as a complete protein. It has all of the amino acids that we need. Plants have a lot of protein as well. It's a misconception to think that only meat has protein. Plants have nucleuses, which contains DNA, which gets converted into RNA, which is translated into protein, just like in animal cells. However, Not all plants contain adequate supplies of all 20 amino acids. Therefore, it's important to get the right mixture. Remembering red beans and rice will help people who do not eat meat, such as vegetarians and vegans, to get all of the amino acids that they need. A proper diet also requires adequate levels of vitamins and certain minerals. These are essential in that we need them. They don't have to come from a plant source. For instance, the body cannot synthesize iron or calcium. We can't generate matter. We must therefore get it from our diet. Minerals may include inorganic ions, such as sodium and chloride, which are very important in the generation of electrical fields, such as within muscle tissue and nervous tissue. We also need a number of metals. For instance, iron is very important to both hemoglobin and to the electron transport chain in our mitochondria. There are a number of other minerals that the body needs for fairly unique situations, like copper and some other odd ones. We usually need these in very low levels. In fact, heavy metals can often be toxic at high levels, and yet sometimes we still need a certain amount of those heavy metals. Vitamins are larger molecules that the body cannot produce, and we therefore must get these molecules from our diet. We can break these down into the fat-soluble vitamins, which are A, D, E, and K, and all of the rest are water-soluble vitamins. A nutrition class can tell you a lot more about why we need the specific vitamins. For our purposes, we need to know that water-soluble vitamins are nearly impossible to overdose on, and that's because the kidneys are just too efficient at filtering out high levels of water-soluble compounds. Exceptions include the heavy metals, which can bioaccumulate in certain tissues, like nervous tissue. This includes iron. Fat-soluble vitamins, on the other hand, are harder for the body to excrete. That's because the kidneys can only excrete water-soluble substances. Nevertheless, overdoses on fat-soluble vitamins are very rare, much less common than overdoses on aspirin, which in turn is even less common than overdoses on acetaminophen. The name vitamin comes from the fact that these were initially discovered as amine-containing compounds, which the body absolutely needed in order to survive. Hence, they were vital. Not all vitamins contain amines, it turns out, and yet the name stuck. The body absolutely needs a certain amount of these vitamins in the diet every day to maintain proper health. One big question is, if we need a certain amount in order to survive, would doubling that amount make us twice as healthy? In fact, Americans seem to believe that. We spend about 20 billion a year on multivitamins, and about half of us take some form of dietary supplement. I suppose the assumption here is that we believe we eat like crap and need to do something about it. Nevertheless, some of the largest studies to date have shown that taking vitamins is not healthy for most people. Certainly, if you have a patient whose blood test shows they have a vitamin deficiency, they absolutely should be taking a vitamin supplement. But everybody else, the effects seem to be minimal. There doesn't, at very least, seem to be any benefit to taking excess amounts of vitamins. I've summarized the data here on the right on one of the largest studies, which looked at people who take multivitamins compared to people who don't. And they asked whether people who take multivitamins live longer, and they found out that they do not. The authors went on to say that this could be due to a problem with how they designed their study. They simply looked at people who did and did not take multivitamins. It remains possible that people who do take multivitamins are already health conscious. Maybe they also eat well and exercise. And if we could just give multivitamins to people who don't eat well and don't exercise as much, maybe there would be a benefit. There's a big problem with that logic, and that is, well, it's wrong. People who take multivitamins, if they're already health conscious and they are already eating right and exercising, we know for a fact they should be living longer. And that's not what the data here suggests. If it was the case that multivitamins could help people who don't eat right and exercise, those people shouldn't be living as long, and a multivitamin should be bumping them up. But that's not what we see. We saw the two groups equal. And if we assume that the group on the right here, the group that's taking a multivitamin regularly, is already eating right and exercising, and I would go one step further. If they're buying multivitamins, they have disposable income, and we know all three of those things are strongly linked to longer life. Eating healthy, exercising, and probably more importantly, being rich. All of those things make you live a lot longer than being poor. So why aren't those people living longer? Well, based on this experiment, it would suggest that it's the multivitamin that's ruining the effects that we see elsewhere of exercising, eating healthy, and living longer. It's also possible that multivitamins don't do anything, and this was just a crappy study. But certainly, that's one conclusion that we could draw from the data as it's presented. What about antioxidants? I know I've been harping on those, and maybe 10 years from now the fad will go away, and I'll have to remove all of those slides from my lectures. But for now, it's still fairly commonly believed that antioxidants are good for us. So why do people believe that so strongly? Well, a lot of very healthy foods contain molecules which can be antioxidants, like vitamin C and E and beta-carotene. In fact, I can't live without those molecules. Certain minerals can also be antioxidants, like selenium and manganese, and these are also good for me, at least at the proper doses. The question is, what about a really high dose? Well, why would we think that antioxidants are good in the first place? And that's because oxidants are molecules that can steal electrons from other molecules, causing their molecular formula to change. If we do that to DNA, that could lead to mutations that cause cancer. And if we do that to lipids, well, we saw that earlier. Oxidizing those polyunsaturated fatty acids could lead to the activation of white blood cells, which can lead to atherosclerosis, making our arteries harder, leading to high blood pressure, which makes the heart work harder, increasing our risk of dying sooner from heart disease. So it would be great to get rid of those oxidation reactions. The problem is, those are the minority of oxidation reactions happening in the human body. For instance, every cell relies on oxidation reactions within the mitochondria to generate ATP. Heck, oxygen is an oxidant. If antioxidants could get rid of my oxygen, I'd be in a world of hurt. So why isn't that oxygen doesn't oxidize all of the molecules in my body? Well, I don't just let it float around, interacting with whatever it wants to interact with. As soon as it dissolves into my bloodstream, I've got hemoglobin picking it up, keeping it away from everything else. And then hemoglobin can dump it off to myoglobin in our muscle tissue, and from there it could be dumped into our mitochondria, where it goes through the electron transport chain, oxidizing glucose, and we can trap some of the energy released in the form of ATP. That's all definitely good, and I certainly wouldn't want to interfere with that by taking some sort of antioxidant supplement. UV damage can also oxidize molecules. That's typically not good, but white blood cells use reactive oxygen species to kill off cancer cells and pathogens like viruses and bacteria. These same reactive oxygen species can also be produced in some of our bodily fluids, like saliva and tears. This helps to protect us against infections. So I think the big question is, if I take an antioxidant, is there any reason to believe it would stop these oxidation reactions without stopping the ones that I really want? And the answer is that no molecule is that smart. Antioxidant-rich diets have been shown to have benefits in people who have diseases where inflammation is causing the damage, such as Alzheimer's disease and diabetes. For everybody else, an antioxidant-rich diet or antioxidants in supplement form provide no benefit. At least no benefit when it comes to heart disease or cancer. And in fact, it seems to increase the risk of dying from certain cancers. That's probably because our immune system uses oxidants to fight cancer. What's more, antioxidants have been shown to reduce the effects of reactive oxygen species that are generated after exercise. And these reactive oxygen species, produced when we exercise, stimulate angiogenesis. Taking supplements to block this is not healthy. We like angiogenesis, and we like the fact that exercise makes our body's muscle tissue stronger, especially cardiac muscle. Before I wrap this topic up, I do want to reiterate something I've said before, and that is many fruits and vegetables contain those chemicals which can be antioxidants. However, you can't eat enough oranges to get that much beta-carotene into your bloodstream to start blocking angiogenesis or to start blocking the oxidation of polyunsaturated fatty acids in our arteries. Therefore, you can't really eat enough oranges to really get a dose of those chemicals where we see them blocking oxidation. And for that reason, you can absolutely keep telling your patients to eat their fruits and vegetables. The problem arises when we increase the dose of those antioxidant compounds to unnatural or abnormal levels. And that's something that you can only do by concentrating them in pill form. The stomach just isn't big enough to hold enough kale or oranges to where those foods could actually be bad for us. With that, though, let's move on to the last topic. And that last topic is hunger. Hunger is pretty complicated. Let's start simply, however. If I eat a bunch of food, that will cause my stomach to stretch, which activates stretch receptors, which signal to the brain, which can reduce our appetite. If everything works properly, if I eat a meal, at some point I should feel full because my stomach is literally full of food. Unfortunately, these stretch receptors adapt fairly readily. Therefore, people who overeat can increase the size of their stomach and decrease the signaling of their stretch receptors in their stomach, meaning they'll be able to fill their stomach up with more food next time before their brain gets the signal. To make things even worse, that's just a small percentage of feeling full, or satiety. To feel full requires a heck of a lot more than stretching out the stomach. It's going to involve a number of hormones and also involve a number of nutrients in the bloodstream, or I should say the absence of those nutrients. Let me start with the hormones. I'm not going to have nearly enough time to cover them all. Let me introduce a couple of new ones. Ghrelin is a hormone produced by the stomach that can increase our appetite. That's the only I'm hungry hormone that I will be talking about. All of the others induce a state of satiety, or a reduction of appetite. Leptin is going to be the new one. This is produced by adipose tissue. CCK, insulin, and a number of other hormones produced around the duodenum and pancreas can also reduce appetite. These hormones should only be produced during the absorptive state, as food is reaching the duodenum or being absorbed into the bloodstream. So the act of getting food to the duodenum should increase our satiety, which is another way of saying decrease our appetite. The hormone leptin has received a lot of press over the past couple of decades. It is produced by adipose tissue, and it can reduce appetite, as well as do a number of other things within the central nervous system that I don't have time to cover. For mice, if you have higher levels of adipose tissue, you will produce higher levels of leptin, and this will reduce your appetite. It's not perfect. If you give mice as much food as they want, they will get obese. But if you inject them with leptin, they won't eat as much, despite the food being there, and they will remain lean. So does this work in people? Well, no, it doesn't. Otherwise, we'd be injecting ourselves with leptin so that we didn't eat as much. So why aren't people as simple as mice? Oh, well, I think I just answered my own question right there. We're not as simple as mice. We do produce leptin. It can reduce appetite, but it seems like our brain is able to adapt to constant levels of leptin. So people who have high levels of adipose tissue, for instance, people who are obese, have higher levels of leptin, but this does not lead to a reduction in appetite, probably because the central nervous system adapts to those constant levels of high blood leptin. More importantly, however, is that the function of leptin in childhood is different from the function of leptin in adulthood. This is true for many hormones. Testosterone, for instance, did something very different to me when I was going through puberty than it is right now. Leptin, when we are children, seems to affect the wiring of the brain, changing how the brain works, causing us to have an elevated appetite or not so much of an elevated appetite throughout the rest of our life. Therefore, exposure to leptin in childhood, or even before we are born, seems to have big effects on how hungry or not hungry we're going to be throughout the rest of our life. Altering leptin signaling in adults is unfortunately too little too late. The body is just too good at regulating the homeostasis of leptin signaling. On the other hand, we can modulate GLP-1. This has been a fairly recent discovery. GLP-1, or glucagon-like peptide 1, is one of those hormones produced in the duodenum when food reaches it from the stomach. One thing that GLP-1 can do is trigger insulin secretion. Insulin, when it reaches the brain, doesn't do what it does when it reaches any cell from the neck down. Usually insulin binding to insulin receptors triggers the increase of insulin removal from the blood entering cells. We don't do this in the brain. We can't store extra glucose. So the brain is constantly pumping all of the glucose that it needs out of the blood into neural tissue, but it's never going to do more. So when the brain receives insulin, specifically the hypothalamus, this usually triggers a reduction in appetite. GLP-1 can do the same thing. So when we activate GLP-1 signaling, this seems to reduce a patient's sense of hunger and helps them to eat less. It also seems to increase insulin sensitivity. This helps people with type 2 diabetes. What's important to note is that while we reduce appetite and increase insulin sensitivity, this doesn't cause patients to lose weight or change their body size. It does, however, help them to keep blood glucose and other dietary effects that are caused by type 2 diabetes under control. It therefore makes them healthier, even though it doesn't necessarily make them quote-unquote look better. So it's not a diet pill. It's a pill that increases a patient's health and well-being. It also inhibits glucagon secretion. And glucagon, as we know, would mobilize blood glucose. And with increased blood glucose levels, this could in turn lead to chronic insulin secretion. Let's go back to leptin and other hormones back when we were children, or even before that, back when we were fetuses inside of our mother's uterus. Our mother's diet affects how our brain is wired. For instance, mothers who are obese during pregnancy are more likely to have children who develop type 2 diabetes later in life. Aha! So it must be simple. Keep moms skinny and everything should be fine, right? Yep, not so fast, Charlie. It turns out the exact opposite causes the same problem. Starvation during pregnancy also leads to children who are at an increased risk of suffering from diabetes and obesity. Our first discovery of this was after we followed the survivors of the Honga Winter. When the Netherlands was invaded by the Germans during World War II, the Germans couldn't defeat the Netherlands, but they could shut off all of their supply of food, and many of the people there starved to death. For those that survived, they had long-term health effects even after they got adequate food supplies. What's more is that the mothers who were pregnant during this starvation time had children who had long-term health effects. And in fact, their children's children are also at an increased risk of type 2 diabetes. This is known as an epigenetic effect. These mothers were not passing on their DNA that led to obesity and diabetes, but these children and their children's children were inheriting something from their mom that wasn't genetic. It wasn't caused by DNA, and that's the epigenetic. This is something, or some things, that we don't understand very well, but we're starting to learn more about. And I think we can summarize it as thus. You can blame your mom for any problems that you have, whether it's obesity or anything else. Now, I say that sarcastically, but in this case, there is some truth to that. And we're learning more about how the methylation of DNA is passed on from generation to generation. And it's starvation and obesity that may lead to changes in how DNA is regulated via methylation that children and grandchildren may inherit from their mothers and grandmothers. The brain also plays a very big role in hunger. For instance, we've learned previously that opioids can activate the nucleus accumbens, causing a state of euphoria. And this is what makes opioids, like fentanyl, addictive. Fat, sugar, and salt in our food can also activate the nucleus accumbens, which leads a lot of people to say that fat is addictive. That was very popular back in the 1990s. Well, we're not saying that so much anymore. In fact, many health food gurus are suggesting that high-fat diets are healthier than low-fat diets. We don't worry about fat being addictive anymore. Today, we worry about glucose being addictive. But for the same reason that it was stupid to call fat addictive back in the 90s, it's stupid to be calling glucose addictive a few decades later. What is addiction? Well, a number of drugs can be addictive, like cocaine, alcohol, nicotine, and opiates. These all directly or nearly directly activate the nucleus accumbens. Lots of things can activate the nucleus accumbens, however. Anything that makes us happy activates the nucleus accumbens, like sex. And yet very few people are sex addicts, even though an orgasm very strongly activates the nucleus accumbens. So why isn't sex addictive? Well, for the same reason that food typically is not addictive. So what is addictive? Well, to say that something is addictive, it really has to be able to do all of these things. Increased use of that compound has to induce cravings. It has to induce a tolerance. Aha. Does anybody ever get a tolerance to sex? Gosh, I hope not. For the same reason that we really don't develop tolerances to fat, sugar, or salt. Addictive chemicals should also lead to binging and dependence. Dependence means that if we avoid those chemicals, it leads to withdrawal effects, which are extreme psychological changes. Well, are we going to go through these withdrawal effects the same if we stop eating fatty foods, the same way we would if we stopped using cocaine? And the answer to that is no. Be careful what you call addictive, is the bottom line here. For anybody who is suffering through addiction or who has survived addiction could potentially be very insulted by anybody else calling things that are really no big deal addictive. Sure, eating fatty foods or sugary foods can activate the same brain regions as opiates and cocaine. However, nobody has ever sold their children into sex slavery to get their next hit off of an Oreo. Therefore, we enjoy fatty foods. We enjoy salty and sugary foods. Yes, absolutely. But I would highly recommend not calling these things addictive. Addiction science won't support you, and many of your patients will despise you if you do. Hunger is primarily regulated by the hypothalamus. It's getting input from the hormones from your duodenum and pancreas. It's getting inputs from the stretch receptors in your stomach. It's also getting inputs from other portions of the brain. Memory is very important in how hungry we are. There have been some very fascinating studies on men who've had their hippocampus removed. These men have anterograde amnesia, meaning they're going to forget everything that happened a few minutes ago. These men were asked to eat a meal, and then 10 minutes later eat another one, and then another one, and then another one. And they never reported feeling full. In fact, it took 4 meals before they said they didn't want to eat anymore, not because they were full, but because they had an upset stomach. So this shows that we can cram a lot of food in the stomach before the brain thinks that it's full. What's more is that the stretching of the stomach is dependent on context. We hardly ever rely on just one of our senses before we perceive something. And the perception of satiety or fullness depends on a lot more than simply stretching out the stomach. If you simply stretch out the stomach, that often confuses the brain. For most of us, if we stretch out the stomach because we ate a big meal, we also remember that we just ate a big meal. Furthermore, our perception of how big of a meal we just ate can also affect our appetite. There's some more very interesting studies on meal size affecting appetite. By simply altering our perception of how big of a meal that we are eating can make us feel fuller sooner. Serving food on smaller plates or serving drinks in thinner but taller glasses can make it appear like we're eating more. Conversely, putting the same amount of food on a really large plate might make us feel like that's a small meal, and it will have less of an ability to make us feel full. So that's a quick tour of hunger. It involves a number of hormones, and I introduced leptin and ghrelin and GLP-1. It involves a bunch of cues from the nervous system, including stretch receptors in the stomach, as well as memory. It involves a number of food cues, such as activation of the nucleus accumbens. It also involves our environment, like how our food is presented to us. So how much of it is willpower? Well, that certainly plays a role, but it's just one part of a very complicated behavior. So that's going to wrap up our chapter. A quick overview of the physiology of our metabolism. Again, I didn't go into nitty-gritty details of the different types of chemicals that we eat. That's more the job of a nutrition class. Here, we really need to focus on what the body is doing with these chemicals and how these chemicals change how our body is behaving. But with that, I'm going to wrap things up.